Imagine a perfect 1-foot square. At each corner is an ant facing its immediate neighbor. At the same exact moment, each ant begins walking towards that neighbor, all at the same pace, and they continue until all 4 ants meet at the center of the square. Assuming the ants to be mathematical points, negligible in size, what distance will each ant travel? To figure this out, let's place the 4 ants back at each corner, and then tilt the square 45 degrees and place it on the Cartesian plane. Now we can focus on the first 2 ants at the 0 and 90-degree positions, and the path they will follow. Each ant begins oriented at a 90-degree rotation from either neighbor, and by continuously approaching that neighbor, the tangent lines of their respective curves will maintain a perpendicular intersection. Let's label a point on this curve xy. Taking a point and applying a quarter-turn rotation will yield a new point, negative yx. That gives us enough information to state the general slope of the tangent line, or the derivative, which is the change in y values over the change in x values. So we have y minus x over x minus negative y, or y minus x over y plus x. We now have a differential equation that describes the curve traced out by each ant. Its variables cannot be separated as is, but since it's homogeneous, we can substitute y with vx. This will allow us to separate the variables. We also need to replace the dy differential with v dx plus x dv. We can now clean up the left side by splitting it into 2 fractions and canceling the dx's. And for the right side, we can factor out the x's and cancel them out. Now subtract v from both sides and combine terms using the common denominator. Distribute the v and then subtract and combine like terms. The v's will cancel out, and if we factor out the negative, we end up with this. We can now easily separate the variables. And then we are ready to integrate. Let's do the right side first. The antiderivative of 1 over x is the natural log of x. And let's go ahead and add the constant of integration c. Now let's focus on the other side. The first thing we want to do is split this integral into 2 separate fractions and integrate each one separately. For the top one, we should recognize 1 over v squared plus 1 as the derivative of arctangent. For the other one, let's do a u substitution. Let u be the denominator v squared plus 1. Therefore, du will be 2v dv. Now divide both sides by 2, and then sub in the u. We can then replace the differential as well. If we factor out the coefficient of 1/2 out of the integral, we are left with the antiderivative of 1 over u, which is the natural log of u. Now that 1/2 coefficient can become the exponent of u, which is the same as the square root of u. We can replace the u with v squared plus 1, and we have now successfully integrated the differential equation. We had initially substituted y with vx, which means the v must be equal to y over x, so we can plug that back in for v. Now let's add ln x to the other side. This is a sum of 2 logarithms, so we can combine them into one single logarithm by multiplying the arguments. Then distribute the x into the radical to get the square root of x squared plus y squared. This equation is written in rectangular form with coordinates in x and y. However, given the nature of this curve, it could be more simply stated in polar form, in terms of a radius and an angle. So let's convert it from rectangular to polar using this original curve. If we draw a right triangle at a given point on the curve, the legs will be x and y. The hypotenuse of that triangle is the radius r, and let's call the angle at the origin theta. The tangent of theta is the opposite side over the adjacent side, or y over x. Therefore, the arctangent of y over x is theta. Let's go ahead and plug that into the equation. Now, using the Pythagorean theorem, we can see that x squared plus y squared equals r squared. which means r is the square root of x squared plus y squared. Plug that in, and we get a much simpler equation in polar form. If we solve for r, we get e to the c minus theta, which is the same as e to the c times e to the negative theta. E to the c is still just a constant, so the e will be absorbed by the c, leaving us with c times e to the negative theta. We now need to figure out what c is. This is a 1-foot square. When the angle is 0, the radius is just half of the diagonal. The diagonal of a unit square is the square root of 2, so the radius is half that, the square root of 2 over 2. Again, that's when the angle theta is 0, so that gives us the value for c. Plug that in, and we finally have the polar equation that describes the curve traced out by one ant. We ultimately want to know the distance traveled by that ant, or the length of this curve. The arc length of any polar curve can be found using this formula. We can see that we will need dr d theta. This is negative root 2 over 2 times e to the negative theta. We also need to square both of these functions for the formula. R squared will give us this, and the derivative squared will give us this. Before we plug these in, let's identify the limits of this integral. We are starting when theta is 0, and we are actually going all the way to infinity. Remember, these are mathematical ants. They have no size or dimension, so we never have to worry about them running into each other. They are merely points on a plane. Now let's plug in r squared, and then dr d theta squared. If we simplify, we end up with the antiderivative of e to the negative theta, which is equal to negative e to the negative theta, evaluated from 0 to infinity. So let's plug in our limits and evaluate. E to the negative infinity is the same as 1 over e to the positive infinity, which is 0. And e to the 0 is 1. And there we have it. The distance traveled by each ant is 1 foot, which was the length of the side of the square they started on. In fact, as long as they always walk in this manner, all at one pace in the same direction and always towards the next ant, the length of their path will equal the side of the square they started on. Thank you for watching, and feel free to like and subscribe.